The controls are ready. Start the reactor.
The reactor is going to power. The reactor is going to power.
This is a nuclear reactor, by name CP5, which means in effect that it is the 5th generation in direct descent from the reactor in which man first sustained a controlled nuclear chain reaction back in 1942 when the atomic age was born. In the years since then, reactors have become among man's most potent and useful research tools. They've taken on many faces, many functions, many challenges. Some already realized, some partially realized, some still dreams. But above all, they serve man in the never-ending challenge to expand his knowledge of the world and of the universe.
Challenge is produced through a grant from the United States Atomic Energy Commission's Argonne National Laboratory.
The primary challenge facing the people who design and build nuclear reactors is to make the energy from atomic fission useful. Some reactors are designed to make power. With others, the production of radiation for scientific research is the goal. CP5 is such a reactor. The man you see is Dr. Bernard Spinrad. For the past 14 years, reactors have been his life.
Since the war, we have been trying to put nuclear energy to whatever services we can find for it. The most common way we have found to apply nuclear energy is through the use of reactors. For the past 10 years, we have been working on central station electric power generation. This work, which started at national laboratories such as Argonne, has been so successful that now there exists a private industry capable of supplying power plants to a utility at costs which are almost the same as normal plants. Similar types of reactors also can produce isotopes, many of which are used for research and many of which are also used for a number of industrial applications. In another way, a similar type of system can be used for propulsion. The most well-known sort of propulsion application is for the nuclear submarines, but we are also completing the NS Savannah, which is a nuclear-powered surface ship. Reactors are unique research devices as well. They have their own unique radiations, and they can be used through these radiations to explore both the nuclear properties of matter and properties of matter in bulk. Finally, more recently, we have come to the application which is the most fun for those of us who develop reactors. This is the use of nuclear power in space for a host of needs which the space program is developing. And since the problems in this space application are harder, since the temperatures required are greater and the neutron populations larger, we are having more fun with this than with any other single application.
Here at the Argonne National Laboratory, the Atomic Energy Commission has focused a great part of its research on reactors. There are 10 of them of various sizes and shapes and for various purposes on the site. 6 more at the laboratory's installation at the National Reactor Testing Station in Idaho round out the complement. To understand their purpose, we must know something about how they operate.
We have here a diagram of the CP5 reactor as seen from the main floor of the building below the level of the control room. We have removed a portion of the external structure in order to show you the details of the inside of the system.
This is William C. Redmond, a senior physicist in the Reactor Engineering Division at Argonne. Dr. Redmond, this reactor looks very complex to me. What's it made of?
Well, for our purposes, we may concentrate only on the essentials. We have in the outermost region, a 4 1/2 foot thick concrete shield to protect the personnel working around the reactor from radiation. We have also a water flow system extending down into the basement for removing and getting rid of the heat produced in the operation of this system. The heart of the reactor, or the core, is contained in the center. It consists of an arrangement of uranium fuel rods submerged in a 6-foot diameter tank filled with water.
What goes on in that tank?
Well, this is where the fission process, or splitting of the uranium atom, occurs. This diagram shows the essential features of the fission process. A neutron strikes and is absorbed by a uranium nucleus, and in the process makes it unstable. It quickly splits into 2 fragments which travel at high energy. Through an atomic type of friction, this energy is transformed into heat. There is emission of gamma rays accompanying this fission process, but more importantly, we get a multiplication of neutrons. Some of these neutrons will leak from the vicinity of the fuel. More will be captured in the system itself, and of those captured, a portion will find other uranium nuclei and be absorbed there, resulting in additional fissions.
How do you maintain the process?
The trick is to make certain that we have more uranium fissions, or at least the same number, in each succeeding generation. We achieve this by designing our system to minimize the leakage of neutrons and the non-productive capture of neutrons. Leakage is minimized by surrounding the core with a reflector for the neutrons. Capture is reduced by choosing materials in which the neutrons have little absorption probability. Thus, we have more neutrons for the fission process.
Can you tell me how you start the reaction?
We find it most convenient to vary the capture rate in order to control a nuclear reactor. A strong absorber of neutrons, cadmium, in the form of blades, passes in between the rows of fuel elements in the water in the core. To start the reactor up, these elements are pulled out of the reactor. Simultaneously, a weak neutron source causes the initial fissions. Because we've reduced capture, there are more neutrons available for subsequent fissions, and quickly the neutron density builds up to the designed operating level.
But once you have started the reaction, then how do you control it?
Well, once our neutron detectors placed around the reactor tell us that we have achieved the neutron intensity for which the system was designed, an automatic control system then matches the output of these detectors to the power demand by moving a weak absorbing rod which passes down into the water of the core.
Then how do you get the neutrons out so that you can use them for your experiments?
Well, those neutrons which leak beyond the vicinity of the fuel and hence are no longer able to help us in maintaining the chain reaction are utilized for experimental purposes. We allow these neutrons to leak out to the experimental apparatus around the reactor through holes passing through the shielding and through regions of low-density material passing also through the shielding. Also, we have a number of thimbles entering the reactor from the top, and in these we can insert samples for the production of radioisotopes.
But all reactors make use of one or more products of the fission process then, energy and neutrons or gamma radiation. Is that right?
Yes, that's right. They differ quite a bit in their appearance and in the internal structure. And in our case, where we're interested in research reactors, we throw the heat away. There are scattered around the United States at various universities and Atomic Energy Commission laboratories nearly 100 research and training type reactors. Indeed, our knowledge of how to use reactors has given us an important tool for the better understanding of the whole world of nuclear physics.
At CP5, scientists are using such a tool. From each of the 8 sides of the reactor projects a maze of experimental equipment. Silently, with unseen efficiency, the reactor generates a steady stream of neutrons. The stream is tapped through holes in the sides.
This is something that you would hardly expect to see in a high school physics laboratory, but it works on the same principle as the familiar spectrometer. In the reactor, we place a sample which is irradiated by the neutrons. The result of this irradiation is gamma radiation, which comes out through a beam hole, emerging in a tight beam from this apparatus here. The gamma rays then strike this crystal, which is a quartz crystal, 1 foot square, bent in a 25-foot circle. According to the wavelength of the gamma rays and the direction of the crystal relative to the direction that they're coming out, gamma rays of certain wavelengths are diffracted into a detection chamber. There they record events on a series of counters which are then electronically represented and fed into a paper chart which the experimenter can see. If the data are going right, he can also produce a paper tape for further processing in a computer.
The spectrometer then sorts out the gamma rays by their energies in the same ways that a spectroscope sorts out the wavelengths of a beam of light.
That's right.
Does it give a rainbow of gamma rays?
No, a rainbow has a constant gradation of one color into the next, whereas the gamma radiations that we measure come in individual sharp lines.
What does the physicist do with the information once he's collected it?
The wavelengths of the gamma radiation are equivalent to energies, which are themselves related to the energy levels of the nuclei. And as a result, the measurement of this gamma radiation can tell us a good deal about the structure, the shape, the amount of deformation, and similar properties of nuclei of all sorts. The information can be useful in other ways as well, because if we know the gamma radiation that results from nuclear events which occur in a reactor, we can then shield against them when we design such a reactor.
In other words, it's like shooting a stream of bullets at an object, except that you want to make sure that some of the bullets stay within the object instead of passing through.
That's right. In this case, in fact, the more energetic the bullet, by and large, the more penetrating power it has. And this is what we want to know. We want to know it not only for gamma rays, but also for neutrons as well. And so, in addition to this crystal spectrometer, we have to measure the neutron energies a device which we call a chopper.
Though it obviously isn't, this apparatus looks like a cannon pointing from the reactor to the far wall of the room. What's that clicking noise?
That's the monitor circuit, which tells us how many neutrons the reactor is putting out for this experiment. The heart of the experiment is up at this end. Inside this massive shield, there's located a rotating member which we call a chopper. It uncovers and covers up again the beam of neutrons from the reactor. As the beam is opened up, the neutrons start a race down this tube. Some of the slower ones are only moving at about a mile a second. Some of the faster ones a good deal more rapidly than that. And they go down the tube and are recorded at several stations outside the building according to their time of arrival. There are 3 stations at 25, 60, and 120 meters, the farthest station being useful for the most energetic neutrons.
Somewhere I read that reactor engineers use the term barn to describe neutron cross-sections. Did you ever tell any of your fellows they couldn't hit the broadside of a barn?
I never did. That story originated, I believe, in the Manhattan Project, when, before much was known about neutron cross-sections, it was feared that they were as low as a billionth of a billionth of a billionth of a square inch. Then it was discovered that they were generally 1,000 times larger, and by that time it seemed as though that was as easy as hitting the side of a barn.
I see. I hadn't realized that the speed of the radiated particles or rays, as well as the very nature of these particles, has a lot to do with the way radiation affects a particular substance. No wonder it takes such a long time to measure all these properties and to study their effects. how on earth do you keep track of the data?
The data actually is brought back here for that purpose. We have several generations of data handling equipment, this being the oldest. At one time, the number of neutrons at any given time after the burst started were recorded on a number of time channels here. Then, as the data started accumulating faster and faster, we went to a magnetic core memory, which could accumulate more data faster for the same purpose. Then, finally, we have this unit here, which records each event on magnetic tape, along with the time of the event and a good deal of other interesting data, both auxiliary and parallel data.
It's an amazing science, shutters that permit bursts of infinitesimal particles at speeds of several thousand miles per hour, crystals and detectors that precisely sort beams of radiation, computer circuits that remember thousands of different kinds of information that are being gathered simultaneously. These are some of the tools that we see around a nuclear reactor. But a reactor is not just useful to the physical scientist. Reactors are making another big contribution in biology. Once we know how radiation affects the processes of life, it will go a long way toward determining the very nature of those processes themselves. A man who has dedicated his research life to finding out how radiation does affect life is Howard Vogel of Argonne's Division of Biological and Medical Research. This is a radiation chamber for the exposure of organisms to external radiations. It was built about 10 years ago, and during that period, a large variety of organisms, both plants and animals, microscopic and macroscopic, have been irradiated with gamma rays and fission neutrons from the reactor. The chamber was built to certain experimental specifications. A large enough exposure area so that an adequate sample of animals for statistical studies could be carried out. A reproducible environmental condition for exposure. A mechanism so that animals could be exposed to either gamma rays or to neutrons or both rays simultaneously in what we call additivity studies. Sir, how will you use this tray of experimental animals in your radiation studies? Well, this is an exposure cage. In this cage, at the present time, 24 animals are loaded. Each one of these is a mouse, and they will be exposed to gamma rays. Dick, would you put this chamber in the tray? The cage is put in a movable mechanism which is motorized and sends the animals into the beam. And then, of course, they are radiated for a given length of time. Then what happens to the animals after they're radiated? Well, the animals then go back to an experimental animal quarters where they are housed in a cage such as this one. Oh, yes. This particular one has 8 mice in this cage. They are put on the shelf and left there for the length of their lives under carefully controlled care and conditions. And then they are studied. Each animal is autopsied on death. But we're not only interested in length of life statistics, we also look for incidence of tumors, for cataracts, for sterility, and even such things as the effects of radiation on general activity and behavior of the animals.
Then you really might say that these little animals act as stand-ins for human beings.
Well, we do learn a great deal from the study of a large number of species of mammals. Such things as permissible doses on man are obtained in this way. We also find out something about the relative biological effectiveness of different radiations. But what we don't know is the effects, the late effects particularly, of very low doses of radiation. And therefore we have built another reactor called Janus at the biology building for the study of such late effects on low doses of neutrons on mammals.
In ancient mythology, Janus was a Roman god to whom was ascribed the origin of all things. He had 2 faces. One depicted youth, the other depicted age. But this complex instrument of steel and concrete does not resemble a Roman god, although it has 2 faces. We're looking down on the reactor. As you can see, it still is under construction. Most of it soon will be encased in concrete. Were Janus in operation, we could not look into its heart as we are now doing. And this is one face of Janus. From an opening, a very wide beam of low-intensity neutrons will emerge from the heart of the reactor. The neutrons will scatter through the air, exposing to radiation each of the occupants of 100 or more animal cages placed on racks throughout the room. These occupants, there may be mice, rabbits, chickens, or guinea pigs, will be exposed to low levels of radiation throughout their entire lifetime. This is the other face of Janus. Dr. Vogel, how will this side of the reactor be used?
This high-level part of the reactor will be used to continue our acute studies, such as the ones we started at CP5. We will do recovery studies after radiation. We will study methods of protecting against the damaging effects of ionizing radiations by using chemical agents, by using antibiotics, or bone marrow transplants.
If I were standing here in front of the reactor during actual operation, how much neutron radiation would I absorb?
If you were standing directly in front of the high-level side of Janus, you would receive a dose of approximately 100 rads a minute. This means that in 5 minutes you would receive a dose sufficient to kill you. At the low-level side, on the other hand, the dose at the front of the thermal column is on the order of 50 rads a week. And at the back of the large room where we saw the animals, it would be a fraction of a rad a week. This means that within the two rooms, we have a range of intensities of approximately 10,000.
Do the neutrons come directly from the reactor?
The neutrons coming from the core of Janus come down the thermal column and impinge upon a uranium converter plate. This converter plate is rising now in the high-level side of Janus. The neutrons then come out into the room from the fission that occurs in the uranium. We have massive shutters on the outside of both rooms which can shut the neutron beam off from either room.
What do you do with the animals after they're exposed?
After the animals are exposed, they're brought back to experimental animal quarters, where they're kept for the rest of their lives. We are interested in studying the effects of neutrons on the whole organism, and therefore an entire range of psychological, behavioral, biochemical, and physiological tests will be used to investigate the biological effects of neutrons on the organisms.
What new information do you expect to get from Janus?
Well, the most important effect will be the effects of neutrons at very low levels on organisms. We're interested in the length of life. We're interested in the incidence of tumors, of cataracts, fertility studies. We will compare the neutron data with gamma data, data from our gamma toxicity program, and thus we will have relative biological effectiveness of the two radiations. Fundamentally, reactors and the neutrons that are produced in them will be used to explain the underlying basic mechanisms of the changes that are brought about by ionizing radiations.
Radiation is a probe. The reactor has a vital assignment, and that is to make abundant radiation available to the scientists. We've seen how some scientists use reactor-produced neutrons to probe the secrets of matter and of life. Let's look at a few. Here is Harold Berger, a metallurgist.
I use a reactor to take pictures of various solids. These look very much like conventional X-ray pictures, except they were taken with neutrons. In many cases, they can provide useful information that X-rays will not reveal.
Walter Kieslewski, biologist.
In Argonne's biology laboratories, I use radioisotopes that are produced in an atomic reactor. I take a substance such as this and place it into an aluminum container, which is then inserted into an atomic reactor. After absorbing neutrons, this substance becomes radioactive. I can then use this material as a miniature radio transmitter in order to study the various processes of life.
Roger Carlson, reactor engineer.
I use a reactor to study new designs and concepts for other reactors. How can neutrons be produced most efficiently in a reactor? Can a reactor be used for space propulsion or to power a manned satellite? These are typical investigations in America's reactor development program.
Joseph Trier, biologist.
Like Walter Kieslewski, I work with radioisotopes in the biology laboratory. But my interest is in using the gamma rays from radioisotopes to alter the processes of life in much the same manner as neutrons are used. A piece of cobalt, about the diameter of a pencil, is bombarded by neutrons in a reactor. This then becomes one of the most potent sources of gamma radiation.
Arnold Friedman, chemist.
I use a reactor as a tool for the production of new man-made chemical elements that were unheard of before the atomic age. The most important of these are the heaviest elements. What are their properties? What are their potential uses? These are questions we are trying to answer.
And Donald Connor, physicist.
My interest is in solid-state science, the science of solids. This is a model of a sodium chloride crystal. The regular arrangement of the atoms in the crystal is responsible for many of the properties of the solid. I use neutrons from a reactor as probes to get inside the solid and study it.
From studies of materials to radiation biology to power for heating and lighting tomorrow's homes, the nuclear reactor, as we have said, has added many facets since that day in 1942 when man first lit the fire. Dr. Spinrad, where is nuclear reactor research taking us?
We're going in several directions which are predictable. For example, we are learning in our researches and investigations into space systems to deal with higher and higher temperatures and unusual environmental conditions. In our experiments on the reactors themselves, we're looking into systems which will give us intense energy pulses, pulses rivaling that of the atomic bomb, but without having any destruction. In the area of research tools, again, we are looking for systems of higher and higher neutron density, which will make more and more intense radiation. What these will mean in the way of application, I don't know. But whenever a research man asks for a crazy specification and we can meet it, we can be sure that an industrial application will follow.
Francis Bacon once said, if a man will begin with certainties, he shall end with doubts. But if he will be content to begin with doubts, he shall end in certainties. And that is the challenge facing nuclear science today.
Appearing for John Fulcrod was Dr. William C. Redmond. Challenge has been produced through a grant from the United States Atomic Energy Commission's Argonne National Laboratory. Argonne National Laboratory is operated by the University of Chicago for the United States Atomic Energy Commission. This has been a Ross McElroy production.
This is NET, National Educational Television.